Hey everyone. So in this video, we're going to be taking a look at infinite limits. So what I'd like to do is start by taking a look at the definition, and then I will do a specific simple example to try and make sense of that definition. And then after that, we'll do a more specific example where we can find the limit as we approach a certain value. So starting with the definition, it says a function f has an infinite limit at c if f is defined everywhere in an open interval containing c, except possibly at c, and f of x becomes unbounded when x is sufficiently close to c. And that last little bit of our definition is what makes this an infinite limit. So let's write this out in notation, and then we'll take a look at a simple example to make sense of this. So what this is saying is we have a limit, and as we approach some value of c, maybe we're approaching from the left, or maybe we're approaching from the right. This definition will apply to both cases. So we're looking at the limit of some function f, and as we get closer and closer to this value of c, f of x, so my function values, are becoming unbounded. What that means is they're getting really, really big, or they're getting really, really small. Very, very positive or very, very negative. So we have notation to indicate that. So what we say is the limit as we approach c, this is approaching infinity. And then the same thing here, maybe this is approaching infinity. That's not the only possibility though. So maybe as we approach from the left, maybe it's becoming unbounded in the negative direction. So in this case, we would say it's approaching negative infinity. And then the same thing for the second one. Okay, so this infinity symbol here, we're only using this to represent the unboundedness of these function values. Infinity is not a number in this case, right? It's not approaching infinity. We're just saying that this limit is unbounded. So these are our four possibilities for infinite limits. So let's make sense of this by taking a look at a specific example. So let's look at the function. We'll say f of x, and this is going to be equal to the equation 1 over x squared. And let's take a look at our limit. So our undefined value here, so when x is 0, my function is undefined. So let's take a look and let's see what the limit is as we approach 0 of our function. All right, I'm gonna look at just the regular two-sided limit here. I wanna see what happens as I approach from the left and as I approach from the right. And let's start by making a table of values to see what happens. Okay, so I have a table, and what I wanna do is I wanna pick out values on either side of 0. I want these values to get closer and closer to 0. So maybe on the left-hand side, we'll start with negative 1/10, so negative 0.1. And then we'll get a little bit closer, and let's do negative 0.01. And then finally, to get even a little bit closer, do 0.001. And why don't we do those same values on the other side, but we'll do the positive ones. So 1,000th, 1/100th, and 1/10th. And we'll take a look to see what happens as we're getting closer to 0. So from the left side here, as we're approaching, this is our limit as we approach 0 from the left. And on the right side here, this will be our limit as x approaches 0 from the right. So I'm going to take each of these values of x, I'm going to plug them into my function. Just to show you the first one, I'm going to end up with, so f of negative 0.1, I have 1 over negative 0.1 squared, which is going to work out. So the negative times a negative, we're going to end up with 1 over positive 1/100th. All right, so now we have a small number in our denominator, and if I'm dividing by a very small number, my result is going to be a number that's larger. So I can think about this like I'm dividing by the reciprocal. So it's like I'm dividing by 1 over 100, so my result is just 100. So here we get 100. Following the same sort of process for my other values, if I plug in negative 1/100th squared, I'm going to end up with 10,000. And for the last one, if I plug that in, I actually end up with 1,000,000. All right, on the other side, I'm plugging in the same values. I just don't have the negatives this time, but our results are the same. So 10,000, and then here we get 1,000,000. So as we can see, as I plug in values for x that are getting closer and closer to 0, right? They're smaller and they're smaller decimals. And when I square them, they become even smaller than that. As we saw with the first one, 1/10 squared, I end up with 1/100th. And I'm taking 1 and I'm dividing it by very, very tiny numbers. So as I get closer and closer to 0, and I'm dividing by these increasingly smaller and smaller numbers, my graph is getting very, very large. My function values are increasing without bound. So here, I'm at 1,000,000. If I pick out something even closer to 0, it's going to be even bigger than that. So I say that this is approaching infinity. It's becoming unbounded. And the same thing from this side. We have the same argument. It's becoming unbounded this way. So what I can say for my final answer then is the limit as x approaches 0 of this function, this is equal to infinity. Now, one important thing to note here is because infinity does not represent a number, technically the limit doesn't exist. For the limit to exist, we need to approach the same number from both sides, the same real number. But in this case, from both sides, we're approaching infinity. So in other words, it's unbounded. So I can still use this notation, but we need to know what this represents. So here, the limit as I approach 0 of my function is unbounded. It's increasing without bound. That's what this represents. If we take a look at the graph of this function, we can also see that as we get closer and closer to 0, our values for our function are increasing without bound. So hopefully now we have an understanding of what these limits are. Let's take a look at a specific example to try it out a little more. So I have the limit as x approaches 3 from the right of this function, 2x plus 1 divided by x minus 3. So the first thing, the domain of this function, if I take a look, the one restriction I have is I don't want to divide by 0. The only value that would make that denominator 0 would be the value 3. So my domain is all real numbers except 3. So if I write this in interval notation, I can say negative infinity all the way up to 3. And then union, picking up on the other side, we have 3 to infinity. So because 3 is not in the domain of our function, we can't just use substitution to figure out this limit. So instead, we need to think about it a little bit differently. Why don't we start off with a table of values for this one as well? Okay, so here's my table. We want to approach 3 from the right. So I'm just going to start with 3 here. And then coming from the right-hand side, we want to pick out values that are closer and closer to that. So maybe we'll start with 3.1, and then we can take a look at 3.01, and then we can take a look at 3.001 and see what we end up with for values. So if I plug these in, so if I plug in 3.1, let's just take a look and see what we end up with. So we have 2 times 3.1 plus 1. That will be divided by 3.1 minus 3. So we're going to end up with 6.2 plus 1 over 1/10. So that gives me 7.2 over 0.1. Okay? I'll get a specific value for that in a second, but let's do one more. Let's look at 3.01. So we have 2 times 3.01 plus 1, and then 3.01 minus 3. Okay, so that gives me 6.02 plus 1, and then 3.01 minus 3, we just get 1/100th. So 7.02 over 1/100th. Okay, and hopefully you can see what's going to happen if I plug in 3.001. So if I look at these denominators for each of these fractions, they're getting smaller and smaller. And again, like I explained in our general example, when I'm dividing by a very small number, my result is going to be a very big number. So as I get closer and closer to 3, the values of these numbers are going to increase without bound. Okay, let's get the results for these. Okay, so I filled in the table of values, and as we can see from our function values here, we have 72, 702, 7002. As we're approaching 3 from the right, these values for my function are increasing without bound. As I get closer and closer to 3, these numbers are going to keep getting bigger and bigger. So I can say that this limit is equal to positive infinity. And again, if we take a look at the graph of this function, and as I come from the right-hand side, I can see that my graph, my function values, are shooting up and they're getting very, very large. So our limit is equal to infinity.